So we start again with Shahram Vatani. Who ordered that?
Yeah. You know who says that? Who said that?
I think for the muon.
Yeah, exactly,
Okay.
exactly. That's why I use this phrase.
Okay.
So when the muon was discovered, Rabi was saying that because it was very weird to have this new particle exactly like the electron, but just a bit more massive. So yeah, it's what I'm gonna talk today. So first, yeah, I start with that. But I had a very pleasant year in GGI. I would like to thank all the GGI people and all the postdocs. I mean, just coming here a few days ago, I realized how beautiful the building is compared to other labs. So other labs are good, but this one is really, it's really something. And I was very glad to have this opportunity here because I could have changed a bit my subject. I never worked on flavor physics, and this talk is going to be about flavor physics. And I would like to start with a quick look on the standard model to put some basis. Because it has been formulated from gauge principle. If you look, we have the weak interactions here on the QCD. And we know from the weak interaction that the matter contents of the standard model is chiral. And if you choose some random fermion representation, there is a lot of chance that you will get some gauge anomalies. And it turned out that we know we study our matters, that so the first family, the lightest state of the standard model, the up and down, the electrons, the neutrino, together they form a family. And this is actually the minimal set of anomaly-free fermion representation that you can have under this gauge group. So it's already a bit remarkable. And then the construction of the standard model keeps going on with an explanation for the electroweak symmetry breaking by use of the Higgs field, which has two benefits. First, it's going to explain the Fermi theory, and also it's going to give mass to the standard model fermion. And all of this process, the guiding principle is gauge. I mean, gauge has been helping us to construct the fermion matter and to build the electroweak symmetry breaking. And along the last century, we've been discovering the muon, the strange, the charm, the tone, and the stop. And all of this matter, it seems that we have 3 times the same family, and this is what we call flavor. We know that there are no 4 family standard model-like, because from precise measurement of Z boson gluon to Higgs, we know that this has to be 3. And this aspect of the standard model is the only one which is not derived by gauge principle. So now that we have this flavor thing, it's very rich because it offers a lot of different hadron, and that you could study and get a huge deep inside the standard model. And if you know those fermions, we assign them family. And first, if you look at how they couple to the electroweak gauge boson from the CK matrix, it seems that it's very natural to assign the top with the bottom, the charm with the strange, and the up with the down. It seems very natural. They couple mainly together to the same electroweak gauge boson. And then we class them just by mass hierarchy. I mean, it's very natural. We say that up, down, they are first generation, charm second, and finally the third. For the lepton, it's another story. I mean, this is not exhibiting the same hierarchy mixing. But we choose naturally to have the same kind of assignment, saying that the electron is the lightest, so it's going to be first generation, the muon will be second, and finally the tau. Actually, we don't care at all. I mean, the physics of the standard model, this is just a choice. You could call the electron from the potato family, you don't care, it's the same. Well, this is true within the standard model. If you go beyond, it's going to be very relevant, the family assignment you're doing. What I'm thinking, for example, is those kind of Paty-Salam unification. So this kind of unification beyond the standard model unify quark and lepton. So quark and lepton, they are now from a single multiplets, and they will be coupled to new physics. And this new physics at lower scale will give you, this model at lower scale will give you the standard model. So the quark and lepton will be separated, but connected through new particle that we call usually leptoquark. In the case of Paty-Salam, those are gauge leptoquark. And now the connection you see that will talk to the same family. So the leptoquark here that will couple to a quark of family X. The lepton here should be family X. So now the way you're assigning the family for the lepton matters. And that's one point. Another point is that if you switch, for example, the tau and the mu, you said they are from different families. So mu will be third, and the tau will be second. You can, as I will show you just after, find a new pattern in the Yukawa sector that will point to a complete different origin for the Yukawa copy. That also might be interesting. So the two things I will develop here is this loop model for masses. And then I will discuss B anomalies. So those are the recent anomalies that have been observed through different experiments. And with the eye of switching the usual family assignment. So let's start with the loop model. So here my assumption is this one. You can see from the color, the mu or no is third family. So same family as bottom and top. Charm, strange, and tau are together. And then the lightest one, it seems very natural to keep them together as the lightest state. And the pattern we can see is that, okay, the first family is of order MEV, second family is of order GV. And for the third family, there is specific patterns. If you look at the ratio of M top over M bottom, you get something very close to 40, and the same for M bottom over M mu. And if you take the ratio sits within 5%. And this indicates a completely different origin of the Yukawa coupling. And you could think that you have an SU2 symmetry between the first two families, which will be breakdown by different spurions with different magnitudes. So very huge magnitude to give you the lightest generation, then a bit less to give you a second generation. But no, the origin for the third generation quark could come from mainly giving mass to the top, and then find a mechanism that will, from the top, give mass to the bottom, and then the mu. One may think, for example, to model with Frogach-Nielsen mechanism, and what I want to show you here is a loop model that can do that. So loop model to generate masses has been studied since a long time. Unfortunately, the most difficult part was to generate the mass for the lightest quark. And here we don't face this problem. What I want we to realize is those ratios. And also, I think there is some novelty in the approach we have, we can discuss later, that was not studied before. It's very subtle, but I think people did not thought about it. So how to generate those ratios? I will add two new scalars at very high scale on that standard model. And this is my Yukawa coupling, so only third generation. So you see, I have the usual top Yukawa coupling, and then I have this Yukawa interaction between my fermion of the third generation and the scalar S and the scalar phi. I included the right-handed neutrino, you will see why very quickly. So from this model, the top mass gets this mass from the Higgs wave, like in the standard model. But now, if you look, this loop that you have within this model is going to generate a mass for the bottoms from the mass of the top. So exactly those coefficients here are the ones that contribute to generating this ratio. What I would like is to have this ratio around 40. 1/40. Now, it's also this model will also generate a Dirac mass for the neutrino, something to keep in mind. This will come from, finally, I have a coupling here that I put in the theory. I could set it to 0 because it will be generated at loop level already. So I just put it here, but actually what I was going to consider is that this is 0, and I will consider only the value of it once it is generated by loop, like here. And from this new coupling here, I can generate the mass of the muon very easily from this diagram. So this is the coupling, this is the loop, and this is the diagram. So you see that this coupling here, that is loop level. So at the end, this diagram is 2 loop level. And this is the ratio you should have between the mass of the mu on the top, and I'm interested in the bottom, but this is loop level. So at the end, I should be able to get the same ratio if, let me go back a bit before, if NR here, the number of neutrino going to the loop, is like NC. I did not explain that. I went a bit fast on the value NC here, which is the number of colors, so 3. Okay, it's very natural to have 3 neutrino. They just need to be light enough compared to the scale of the scalars, so that should be okay. Plugging some consideration, so my neutrino here, as I have right-handed on Dirac mass, will get a mass from a seesaw mechanism. I want the mass of the right-handed neutrino to be below the mass of the scalar. And now if I plug just some usual simple consideration, mass of neutrino, electron volt, 3 right-handed neutrino, coupling of those order 1, what I get is a model of like this. This indicates the mass of the right-handed neutrino, the ratio of the mass of my 2 scalars, and that gives me a hint for the scale lambda. So what we checked is that this kind of model could be very dangerous for proton decay, and we checked that proton decay will be above this bound, so there's no issue. So this is really a toy model. What I wanted to emphasize that it can very easily explain the pattern we have, and for sure, I mean, lack of UV completion, but this was a way to show you that the idea of having the muon in the third generation is nothing crazy at all. But what I'm also very interesting now is to show you that this can actually fit some of the flavor anomalies we have within the standard model. So to tell you a bit about that, I'd like to highlight first RK. So this is a ratio of 2 branching ratio we have in the standard model of a B decay to a kaon on 2 leptons, so muon versus electron. So standard model prediction tells you that this should be roughly very close to 1. The discrepancy in front should be very small. And what we observe is something 3 sigma below. And this also, I like this observable because it's a clean observable in the sense that it's not very sensitive to the QCD radiative correction. Then you have the decay of BS to mu mu. So this one also, experimentally, we observe decrease compared to the standard model prediction. And again, this should be clean from QCD correction. So this is just the 2 main that I clean and I wanted to highlight. People on the flavor physics very often looked at them. Then in the rest, of course, I took other anomalies into account, but I just wanted to give you some insight of what's happening in flavor physics. So to study those anomalies, there is a low energy effective field theory of the standard model, which is the perfect framework to study that. What has been highlighted, there is a specific set of ortho interaction that can explain those anomalies. And especially those, for example, this operator O9 and O10, which connect strange on bottom to 2 muons. So it seems that we need to decrease of the Wilson coefficient of this operator to match with the anomalies. Just to give you some examples. That's the kind of operator we would like to be able to generate. And a way to generate that is to consider leptoquark, as I was showing you before. So leptoquark, they connect to a quark on a lepton. So if you integrate out, you get a 4-fermi interaction between 2 quarks, 2 leptons. And there was a very successful model, a UV, mainly almost UV complete model up to very high scale that was trying to do that. And I'm going to present it to you. It's going to be a bit far away of the idea of muon in the 3rd generation switching, but then you will get the point. So a bit introduction to the kind of model trying to solve those anomalies. So the idea is to start with 3 standard model-like unified families a la Patti Salam. So as I was saying, I unify quark and lepton in 3 families. To avoid confusion, I call them A, B, and C. And this is at very high scale lambda OV. Then I have also a bunch of scalars that's going to give me some breaking. And at lower scale, I will break the Patti Salam unification for family A and B. So here I'm almost at the standard model level, the way those behaves. But this is still at a very high scale, considering what we are probing in the LHC, etc. So even lower scale, now I have the breaking of the 3rd family, the family C. What this tells us is that here you should have leptoquarks that are generated and coupled to them. But this is very high scale, we should not be sensitive to. However, the one here, I want the scale here to give significant marks on what we are probing at right now. So there will be a leptoquark that will be connected to the quark and lepton from family C, which means that you will be able to generate those kind of four-form interaction with forces. So the thing is that this model, as there is some scalars on a more complicated dynamic than just three families, will also generate some mixing. So they will generate a Yukawa coupling between the, so this has to be thinking in terms of 3x3 matrices in the ABC flavor space. And this kind of Yukawa coupling, this is typically the kind of Yukawa coupling you could expect in those models, with epsilon 1, very small compared to epsilon 2, very small compared to epsilon 3. And what does it tell you is that the family C here should be the most massive one. Then you should have family B, sorry, and finally family A. And this is the kind of mixing you will expect, for example, between family B and C. And what this means is that if you want to convert a C to a B, you need to pay a price of epsilon 3. And this has actually been used. So I start with my four-form interaction between 4C, and I convert a C to a B. So that's just paying the price epsilon 3. If I want to convert two C to two Bs, epsilon 3 squared. No, this was really, I mean, I trying to sketch a bit the dynamic. If we go back to the observable that it matters for flavor physics, this kind of observable operator, sorry. Here I have a strange and two muons. This is second family within standard model, which means that you have 3 times with second family, you have to take epsilon 3 to the cube, because the bottom here is third family. So you get a suppression, but that's okay because the leading operator you are creating will be only talking to third family, which we are not very sensitive right now at LHC. So this helps us to reduce the scale of the breaking, and also just to, in order to get the right amount for this coefficient. And okay, this works very well. I have nothing bad to say. I mean, actually, I find if you look into the detail, this is a very beautiful model, but there is this assumption of the Yukawa coupling. And if you look in details how this model works, you could change this matrix to the matrix like this. I think this is completely acceptable within the model to have actually at the end a Yukawa coupling, which looks like this. And what appears here is that it's not the most massive particle is placed here. I mean, this is the mass of the most massive family eigenstate you should have. It means that if you know that in standard model, it's a tau lepton. So it means that the tau left will be in the second family. The second heavier particle, which is a muon. No, it's here. It should be epsilon 3. I'm keeping the same order between epsilon 1, like smaller than epsilon 2, smaller than epsilon 3. So now the muon here, only the left part should be in third family. That's what I'm thinking. And this is completely acceptable within the dynamic they have. If you do that, a very nice thing that you can do is that you can use the paper, change a bit that, and recompute all the observable that you need to consider in flavor physics. And this is what we've been doing. So here I'm going to show you the results. So here I plot RK, the first observable I was concerned. Here is BS to mu mu. And within the black curve, this is the parameter region that is low. Now I'm going to put some constraints from all the observable we know. So there is the delta F equal to observable, which is mixing between when you switch two flavor of the quarks. This is going to be with 95% of confidence level. That's going to put me in this region. For those who are interested, in this, there is a lot of different observable in this constraint that's containing here, but mainly one is driven on delimiting this region is BS bar mixing. Then you have lepton flavor violation. So again, there is a lot of observable within this class of observable, but the main one that is going to give me the constraint is the decay of tau to 3 mu. And then you have lepton universality, but actually the whole region is completely within the bound of lepton universality, so I'm not going to put it. So at the end, that model is going to tell me that with 95% of confidence level, I could be somewhere here, which is quite good, actually, compared to the data. I'm taking a very extreme approach for our case. So this is, it's a very good prediction within the model. And something which is a bit nicer from here, that from the first model I showed you, is that they had to add some specific operator to the beautiful unification they were doing in order to generate the anomalies. Here, I'm not changing anything. I'm starting with 3 copies of the standard model. And the only thing I'm saying is that their assumption on the dynamic should give me a different Yukawa pattern. And this Yukawa pattern can predict exactly the anomalies within good agreement. So I hope that in this, I don't know if I was on time. Okay, perfect. What I wanted to show you is that the family assignment within the standard model, okay, doesn't matter. But if you're going beyond, it actually matters a lot, and you can do many things with it. And I hope those 2 examples illustrated that very well. So thanks a lot for listening. And if you have any questions.
Thank you. Thank you, Shahram.
So unfortunately, all the particle physicists went already out.
No, not all of them.
Yeah, it's true.
Do you have a question, Michele? No, I have a question. What about
in that case, it's very small. It's yeah, I cannot agree with German. Also, I don't know how much we can.
Otherwise, it's being.
Yeah, German too. It's an interesting story, but I think I mean we need more results from lattice the community to help us.
That's true. No, I mean with this model.
Yeah,
that's
so
true.
In this model, no.
It's not
without this model or the model from the basics model at the beginning, which I did not say where it's coming from. It's from a group in Zurich. With even their model, it's not really improving humanity.
Yeah. Okay. Yes.
Just wondering, one of the slides you have this matrix Y.
Yeah.
Maybe the next one, maybe.
I know it was.
Yeah. Stop. Yes, exactly. So you have the. I didn't understand why there's arrow from the first one to the second, because they have different trees, right? They are not.
No. This is what they have in the first model that I was explaining. So, and this what I'm saying is that the setup they have could give you a different matrix. So I'm going through another.
So if you swap the row of this.
No, it's not swapping the row. It just so you need to take into account a bit what is the dynamic that is going to generate this matrix.
Okay.
And what I'm saying is that this dynamics could generate a matrix with this kind of hierarchy. What matters really is the hierarchy. Where are the coupling? What are the dominant entries and subdominant entries?
Okay. Yeah. Thank you.
So yeah, this is I just wanted to say that what they obtain, you could find another pattern, which should be I think it's acceptable. I don't know what they think about it. The paper will be out very soon. But I think it's completely acceptable to have this new structure.
So I have a general question. I want to ask you, this is like a weakly coupled way of thinking of the generation of 09, right? Because they're integrated out scalar to get to achieve the weakly coupled model to generate those operators, right?
Yeah.
Very generally, I wanted to know if there are some strongly coupled attempts to do this and how to compare.
So by strongly coupled, you're saying that like a new strong sector that generate this kind of.
Yeah, where it's not generated by directly integrating out something.
I think most of the model they are based on leptoquark. I mean, I'm a bit new in this world, but I think the most trendy thing is to use leptoquark. So a state which is heavy that you integrate out and then you use generator. Okay. There are some attempts to gauge some part. No, it's not completely true. No, you have some attempts to gauge to add new symmetries to the standard model that you gauge, like you consider like U1 symmetry for the U1X symmetry, where X could be one of the difference of leptonic numbers. But at the end, you do that, but you introduce a new gauge boson. So I think at the end, it's more or less equivalent.
Okay, thank you.
No other question. Thank you, Shahram. Thank you very much.